A spacecraft launched when Jimmy Carter was president has just spent nearly 50 years sending messages back from a place no human being has ever reached. It has traveled farther than every planet in the solar system, farther than the solar wind itself, farther than any human-made object in history, except for its twin launched just weeks earlier on a faster path. And from a region where scientists expected one kind of environment, Voyager 2 found something else entirely. A boundary that did not behave the way decades of theory said it should, and a region beyond it that turned out to be far stranger than anyone had planned for. The question this raises is not simply what Voyager found out there. The question is whether we ever really understood where our solar system ends and what begins beyond it. A machine leaves everything familiar behind. In the late summer of 1977, two nearly identical spacecraft left Earth within weeks of each other. Voyager 2 launched first on a slower trajectory, while Voyager 1 followed shortly after on a faster path that would actually put it ahead. Both carried a now famous golden record, a time capsule of sounds and images meant to represent humanity. At the time, human understanding of the outer solar system was remarkably thin. Spacecraft had visited Mars and Venus, but no probe had ever flown past Jupiter, Saturn, Uranus, or Neptune. Most of what scientists knew about these worlds came from blurry telescope images and educated guesswork. Voyager 2's original mission was to fly past Jupiter and Saturn, gather as much data as possible, and then most likely fall silent. Nobody designed it to last half a century or to leave the solar system entirely. It was built to answer a handful of questions about two planets using technology that by today's standards is almost unimaginably modest. But a rare planetary alignment in the late 1970s opened a window that would not reappear for well over a century. If Voyager 2 survived its encounters with Jupiter and Saturn, the same gravitational assist could in principle carry it on to Uranus and Neptune as well. Engineers began quietly hoping for something the original mission had never promised, a mission that refused to end. Voyager 2 reached Jupiter in 1979 and revealed volcanic activity on the Moon, IEO. It also revealed storm systems on a scale no one had previously documented. Voyager 2 reached Saturn in 1981 and returned detailed images of the planet's rings. Those images reshaped how scientists understood ring structure and composition. By any reasonable standard, the mission had already succeeded beyond expectations, and yet Voyager 2 kept going. In 1986, it became the only spacecraft to fly past Uranus, and it discovered new moons. It found a tilted magnetic field unlike anything at the other gas giants. In 1989, Voyager 2 reached Neptune, returning the first close-up images of that distant world. To this day, Voyager 2 remains the only spacecraft ever to visit either Uranus or Neptune. After Neptune, there were no more planets to visit, and mission planners faced an unusual problem. The spacecraft still worked and still had power, but nowhere obvious left to go except outward. So Voyager 2 was redirected toward the edge of the sun's influence, the heliopause. Decades passed, and generations of the original mission team retired while Voyager 2 kept moving. On November 5, 2018, Voyager 2 recorded a sudden sharp jump in plasma density at about 119 astronomical units. The change was roughly 20-fold higher than the thin solar wind plasma it had been flying through. It was the unambiguous signature scientists had been waiting for. Voyager 2 had crossed the heliopause into interstellar space. On the surface, this sounded like confirmation of existing models, but the details told a stranger story. 6 years earlier, Voyager 1 had crossed the same kind of boundary, roughly 10 astronomical units farther from the Sun than Voyager 2 eventually did. The difference was significant because the two spacecraft left the solar system in almost opposite directions. Some researchers had actually expected Voyager 2 to cross first based on heliosphere models built from Voyager 1's data. The size mismatch revealed something models hadn't fully captured. The bubble surrounding our solar system isn't a clean, symmetrical sphere. It is lopsided, irregular, and apparently still being reshaped in ways scientists are working to fully explain. As Voyager 1 crossed its boundary in 2012, its magnetic field readings didn't shift direction the way theory predicted they should. For months, the data was so confusing that scientists informally nicknamed the region the Helio Cliff, unsure whether the spacecraft had truly left the solar system. The eventual explanation involved interstellar magnetic field lines draping around the heliopause rather than crossing cleanly through it. This revealed a far more complicated geometry than anyone had assumed going in. And then there was the temperature just outside the heliopause, which surprised scientists again. Instruments on both Voyagers detected plasma at extreme temperatures, sometimes exceeding tens of thousands of degrees. Under ordinary circumstances, such temperatures should have posed a serious risk to onboard electronics. The spacecraft survived because the plasma, despite its blistering temperature, is so sparse that it carries almost no heat to transfer. But the temperature reading itself was higher than existing models had predicted, suggesting our picture of local interstellar conditions was incomplete. A boundary that was supposed to mark a clean exit from the solar system was instead proving to be asymmetrical, geometrically strange, and thermally extreme. Perhaps the most important shift from Voyager 2's crossing is this. Interstellar space is not the dead, featureless void it is often imagined to be. Data from both Voyagers show that just outside the heliopause, plasma piles up, slows down, and heats up in a relatively narrow boundary layer. On the inside of that boundary, instruments detected a faint but measurable trickle of particles from inside the heliosphere leaking outward into interstellar space. It is as though the boundary separating our solar system from everything beyond it isn't a sealed wall, but something closer to a porous membrane. The interstellar medium Voyager 2 reached turned out to be variable rather than uniform, with density and temperature shifting in unexpected ways. These variations suggest the medium is shaped by unseen structures, possibly including lingering plasma from ancient supernovae in this part of the galaxy. None of this matches the simple image of leaving the solar system as a single clean moment where one environment ends and another begins. Voyager 2's data describes crossing through layers of an active, structured, and still changing boundary zone shaped by the sun and the surrounding galaxy. The heliosphere behaves less like a fixed wall and more like a breathing membrane, expanding, contracting, and leaking in response to forces on both sides. As of 2026, both Voyager spacecraft are still operating, although barely. Their power sources are radioisotope generators that convert heat from decaying plutonium into electricity, and they have been losing power every year since launch. To stretch the mission, engineers have shut down one science instrument at a time on each spacecraft to keep the rest operating a little longer. It is a strange ending. Not sudden failure, but a slow, carefully managed fade, instrument by instrument, watt by watt. Two machines older than the internet continue radioing home from outside the sun's influence. Voyager 2 taught us more than measurements about plasma or magnetic fields. It taught us that the edge of the solar system is not a line on a map. It is a dynamic, structured, and still poorly understood frontier that reveals new complications whenever something actually crosses it. For most of human history, the edge of our solar system was pure speculation, a boundary nobody could see, test, or measure. Voyager 2 changed that by showing how much of our understanding was incomplete rather than simply confirming expectations. The boundary proved lopsided and geometrically strange rather than symmetrical and clean. The plasma beyond it turned out to be hotter, more variable, and more structure than existing models allowed for. Decades after launch, with most original instruments silent and power fading, Voyager 2 still teaches us the lesson it taught when it left Neptune. The solar system does not end where textbooks once said it did. And the farther we manage to look, the stranger that frontier keeps becoming.